All right, welcome back. I'm going to continue with our review of Unit 2, and this video is going to review our process of regression. In this particular example, number 3, we're actually combining what we know about sequences with determining a regression model using our calculator. So in number 3, it says a pool manager wanted to emphasize to lifeguards the importance of treating the swimming pool with chemicals at regular intervals. He performed an experiment by releasing bacteria into a swimming pool and leaving the pool untreated for several hours. The table below shows the growth in the number of a certain bacteria in the swimming pool at various times. Notice that we have 3 rows here. We have an N in terms where it's just listed as 1, 2, 3, and 4. This is to help us with the sequences. And this is going to correspond to problems 1 and 2, because in in A and B, let me fix that. Because in the first 2 parts of this problem, you're asked about coming up with a recursive formula and an explicit formula. So we're looking at for the number of bacteria. So we're basically just looking at that single variable, the number of bacteria and how it's changing. So if we're going to model with a recursive formula, first of all, we have to determine whether or not we're dealing with an arithmetic or a geometric sequence. Well, if I look at these numbers, to go from 600 to 900, that's a difference of 300. To go from 900 to 1350, that's a difference of over 600. So, of over 400. So I can tell right away that this can't be arithmetic. So I'm guessing that it's probably going to be geometric. And so in order to confirm that, I need to figure out if there's a constant ratio or a common ratio. So I'm going to start with my 900. Because remember, we always start with the second term and then divide it by the first. And that gives me 1.5. So let me try the next one. 1350 divided by 900. 1.5. Great. And then 2025 divided by 1350. And hopefully I'll see 1.5. I do. So that confirms that I'm dealing with a geometric sequence. I know that my first term is 600. And we've just determined that our common ratio is 1.5. So I'm pretty much going back to what I did in problem 2 here to write my recursive formula. So remember, our recursive formula has 2 parts. We have to decide where the sequence begins, which is at 600. And then we have to write a rule for determining the next term. And so if I just call that a sub n plus 1, I know that my rule for finding the next term depends on what the term was before it, which the term before n plus 1 is going to be n. And I'm just going to multiply that by 1.5. So that's my recursive formula. The explicit formula, remember, combines the first term and the rate of change together into one formula. And we call that a sub n. And so I know I'm starting at 600. And after that, I'm just multiplying everything times 1.5. To make it a rule, though, I need to include an exponent of n minus 1. So that's using what we know about sequences. Letter C is asking me something different. It says to model the number of bacteria as a function over time. So now I'm introducing a second variable. Let me do this in another color. Now I'm looking at the relationship between time and the bacteria. So I'm looking at 2 variables here. When I'm looking at 2 variables, now I'm talking about doing regression. And so I've got to think about what pattern I'm looking at. Well, if you remember, we said a geometric sequence is going to correspond to an exponential regression or an exponential function. Okay, if it's arithmetic, it would correspond to a linear model. So what I'm going to do is enter in the elapsed time and the number of bacteria. I don't need to worry about the n. We put that there so that you wouldn't be confused about the terms in the sequence. So if I look just at elapsed time, I'm going to have to go in and enter the data into my lists. So let me go ahead and delete what's in there. And so in list 1, I'm going to have 2, 4, 6, and 8. And then in list 2, I'll have 600, 900, 1350, and 2025. Okay. And so just to confirm that this would be modeled by an exponential function, I'm going to construct a scatter plot so you can see. So if I go into my second y equals, I'm going to go ahead and select one of my plots to turn on. I want to make sure that I'm choosing my scatter plot option and that I'm calling my data from the appropriate list. So all my X values are in list 1, so I'm going to change that to list 1. And all my Y values, that's going to correspond to the number of bacteria, are in Y2. The next thing I want to do is just double check to make sure I don't have any equations. Oops. In my y equals. And so if I go into y equals, I can see that that's clear, and that's great. I'm not going to have any equations left over from other problems that are going to interfere with my plot. So to graph my scatter plot, since I've entered data, I'm going to hit Zoom Statistics, which is the same as Zoom and then option 9. Okay. Now, even though with those 4 points it may actually look like it could be modeled with a linear equation, because we know that this is a geometric sequence, I want to make sure that I'm doing exponential regression. So please remember that for this problem, since it's a geometric sequence, you're going to want to do exponential regression. If it were an arithmetic sequence, then you'd want to do linear regression. So let me write that down. If it's arithmetic, then you're going to do linear regression. Okay, if it's geometric, then you're going to want to do exponential regression. Okay, so I'm going to go ahead back to my home screen, because this is where I'm going to do my, to come up with the equation. I'm going to go to Stat, because I'm dealing with statistics. I want the calculator to calculate the regression equation. So this time I am going to scroll down until I see exponential regression. There we go. And I need to tell the calculator where my data is. Now, the calculator will automatically default to list 1 and list 2. But if it's not there, then you need to make sure you type in list 1 and list 2. If you have an older calculator, you're going to write list 1 and then put a comma and then list 2. We also want to store the regression equation into y equals. So here's where I'm going to enter in my y. I want to put in y1. So I have to hit the variable. Y variables, it's a function, and then I choose the equation that I want to paste it into. If you have an older calculator, it's just going to be the sequence of commands. It's going to be list 1, comma, list 2, comma, y1. Okay, and so now I'm given the equation. And now instead of writing it a sub n, I'm going to use my y, because now it's going to be in terms of x and y. And so I'm going to go ahead and type in 400, and then my b value is 1.22. I'm going to round that to a 5, and that's going to be to the x power. Letter D says to sketch the graph of your model from part C. So if I go to my graph now, I can see that equation. It says to describe the key features, including intercepts, maximum and minimum values, asymptotes, whatever. It also says to state the domain of the function and is it continuous or discrete. So in this case, I'm only seeing a short part of my graph. I'm going to actually want to rescale it so I can see the origin. So if I go to my window, I'm going to actually make my x min, I'm going to make it negative, let me go ahead and just make it -5, and I'm going to let this go up to 15. And then with my y min, I'm also going to make that, I'm going to make that -5 as well. And I'm going to let the max go up. I'm going to round that to 2,500. And I'm just going to do this so it's neat. All right, so what I have here, let me actually do this in a different color. It looks something like that. And if I go to my window settings, you don't have to do this. I don't think you're going to be asked to do this on the calculator, but on the test, but I'm going to go ahead and just put my min and my max values in here so that you guys can see the scale that I used. Okay, so now it says to identify some important features of the graph. And by important features, we're looking at intercepts, maximum, minimum values, and asymptotes. Well, what you need to remember about an exponential function is that every exponential function has a horizontal asymptote. And that horizontal asymptote is always going to correspond to the value of k if we think about our transformed function. So if you look at my equation, this number here is my value of a. If I look in terms of h and k, my h is just 0 as well as my k value. I'm not shifting the graph left or right at all. All I'm doing is dilating the parent function. So my asymptote, so I have a horizontal asymptote, and that's just y equals 0. That's that blue dotted line that I drew. There is not going to be a minimum value because my function is just going to keep getting closer and closer and closer to y equals 0, but it's never going to touch it. So there is no min. And notice that my function goes on increasing forever. So there is no min or max. It also asks me to identify any intercepts. Well, the graph is not going to cross the x-axis, but I can identify my y-intercept here. And remember, the y-intercept occurs when x is equal to 0. Well, think about it. If I plug a 0 into my equation, you can do this a couple different ways. If I plug a 0 into my equation, I have 400 times 1.255, or 225, sorry, to the 0 power, and notice I get 400. My 0, my y-intercept is going to correspond to that a value. So my y-intercept is 400. There is no x-intercept. The other question is asking me to state the domain. Well, in this case, in every exponential function, the domain is all real numbers. However, for my model, we need to be very careful because I'm not just talking about the exponential equation y equals 400 times 1.225 to the x. With my model, remember, it's only good at predicting values for the data that I've collected. So I want to be careful when I'm describing the domain. It's only my model, and I think it even asks, state the domain of your model, not of the exponential function, but of the model. My model is only good for the time frame from 2 to 8 hours. So I'm just going to specify that it's only good for that time frame. And this is, if you remember the writing assignment that you guys had with the argumentative writing, and we made a prediction that was way beyond our data, even if this is a perfect model, which it is, it hits every single data value. Even though it's a perfect model, because I don't have data beyond 8 hours, I don't really know what happens to the number of bacteria after that. I can certainly mathematically use the equation and solve and answer some questions, but I'm not going to be really confident of my model beyond 8 hours. So when it asks about the domain of your model, you want to make sure that you specify that the model itself really is only good from 2 to 8 hours. So in letter D, it says, suppose you're the pool manager. What mathematics would you use to describe the growth of bacteria? Well, notice this is my rate of growth. So every hour, now notice in the table it's every 2 hours. So every 2 hours, the rate of growth would be 1.5 times. But if I look at my rate of growth for my exponential function, every hour, the number of bacteria I'm just going to say multiplies by 1.225. Another way of saying that would be it's a 22.5% increase. If you wanted to use a percentage. It doesn't matter to me. If you want to just spell it out, every hour the number of bacteria multiplies by 1.225. That's the clearest and easiest and most simplified way to describe the change in the bacteria or the rate of bacteria growth. If you want to change it to a percentage, that's fine. That means that basically every hour there's another 122% or 22.5% in the pool. But you can just write it as a multiple of 1.225 is fine. If left untreated, how many bacteria would be in the pool in 18 hours? So here's where I'm just going to let x equal 18 and plug it in. There's lots of different ways you can do that. I can go to my table, for example. If I go to second table, I can just scroll up and down until I see where x is 18. And that tells me that when x is 18, the number of bacteria is 15,000 377. Now, I'm not really confident in that because my model's not really good beyond 8 hours, but it's not asking me that. In letter F, it said if the bacteria reaches a count of 34,600, then it's unsafe for swimming. Approximately how many hours could the pool be left untreated before it would be unsafe for swimming? So this time, I'm giving you the y value. So we're going to let y equal 34,600. And so if I'm going to enter in a y value, the only place to do that is in my y equals screen. So what I'm going to do is need to add a second equation for 34,600. And now we're looking at solving a system of equations. If I go back to my graph, though, you'll notice I don't see the second equation. And that's in my equation for y equals 34,000 should be a horizontal line, but I don't see it. And if I go to my window, that'll tell you why. Notice that my y max is only 2,500. I need it to go all the way up to 34,000. So what I can do is just enter, or change this, actually. Let's go ahead and change it to 35,000. And that way it'll be bigger than the value of y that I need it to be. Now if I'm going to increase my y, I'm probably going to need to increase my x as well. So I'm going to increase my x, let's just say to 25. And so if I go to my window, what I'm hoping to see is the same curve of my bacteria growth, but I'm hoping to also see, there we go, that 34,600. And as long as I can see the point of intersection on my calculator, I can calculate it. If I go to second trace, notice there's an intersect option. Now look at the commands, or look at the questions that the calculator is asking me. What is the first curve? So I could plot like 6 different graphs on here if I wanted. I have to tell the calculator which curves I'm trying to find the intersection for. So I only have 2 on my graph, so when it asks for the first curve, I can go ahead and hit enter. Notice now it's asking me for the second curve. Well, now the second curve, notice where my cursor is on Y2. I'm going to press enter again. For whatever reason, the calculator lets me guess. I'm not interested in your guesses, though, so press enter one more time. And as soon as you see the intersection, you can see the value of x. X is equal to 22, or 22 hours. Okay, now it doesn't ask in this problem, but I'd want to be very careful about making predictions that are this far beyond my data. Okay, I'm not confident of my model at this point. Okay, but that's how you would answer those questions. All right, and number 4, it says natural resources scientists have been collecting data on a hazardous waste spill from many years ago. The table below shows the amount of the hazardous waste remaining over time in days. So notice how the x value in this case has been written in scientific notation. So you can enter these in your calculator just like they're written here in the table, and I'm going to show you how to do that in just a second. We also have the amount of the waste that's left. So notice that the amount of waste is getting smaller. It's decaying. So letter A is asking us to do exponential regression to model the data in the table. So again, I'm going to go ahead into my lists, and let me clear out what's in there. And you should be doing this with me. So obviously after 0 days, so that would be at the beginning or the initial spill. And then for the next one, I just want to do 1 times 10 to the third. I can enter it just the way it appears. Notice that's just 1,000. My next one is 2 times 10 to the third. That's going to be 2,000. 3 times 10 to the third, you can imagine, is just going to be 3,000. But don't let the scientific notation confuse you. Just type it in the way you see it. Okay, and the calculator will evaluate that for you. The amount of waste, so we've got 15,000. I guess that's grams. And then it decayed to 11,250, to 8,500, to 6,500, to 4,750, and to 3,500. Okay. In order to come up with an exponential regression equation, let's go ahead and just graph this so you can see what it looks like. If you remember, I had some equations in y equals that I want to go ahead and clear out now. And my stat plot is already set up to create a scatter plot with the data in list 1 and list 2. So all I really need to do is zoom 9 it again. I have different statistics, so I need to rescale my axes. So again, this does look fairly straight, but we're told to do exponential regression. And so if I go back to my home screen, we're going to go to Stat, Calc, and then scroll down until you see exponential regression. And again, I want to make sure I let the calculator know where my data is. X's are in list 1, Y's are in list 2. Ignore the frequency list, and I'm going to store this in Y1. So I'm going to go to vars, Y vars. It's a function. I'm going to store it in Y1. All right, and the equation that I get is going to be Y equals, the A value is 15,112.694. And my B value is 0.9997. And that will be raised to the X power. Letter B says the chemical company that produced the hazardous waste claims the waste will decay according to the following model. So let's look at their equation. It's Y equals P times 3 to the negative, I'm sorry, I can hardly see what that says. Let's see. To the negative 1 over 3,800 times T. Okay? Well, if I take a look at this, this is just an exponential equation because I've got an exponent with a variable in it. But I can just look at this. If I take all the number part of that term and evaluate just that number part, I can also write this equation in a different way. We know that P is the initial amount of waste in grams and T is measured in days. It says to compare the bases of the two models. The base is this number here. It's the term that's being raised to the power. When we were dealing with sequences, we called it the ratio. Well, the base in my second model is just this, 3 to the negative 1 over 3,800. So I'm just going to evaluate that on my calculator. 3 raised to the negative 1, and actually let me put this in parentheses. So negative 1 divided by 3,800. Pull that out of the exponent, and when I press enter, what do you notice? The bases are the same. Oops, are the same. Okay, so I do want to just point out that sometimes with exponential functions, there's more going on in the exponent than meets the eye. So for example, if I have, say, y equals, I don't know, I'm just going to make up something. All right, so let's say I have that as my exponential equation, and I'm asking you, what is the base? The base is simply 2 to the negative 14 over 12. Because I can essentially rewrite this as 2 to the negative 14 over 12 to the t power. Okay, and it means the same thing. And so if I wanted to evaluate the base, I would just say 2 raised to the, and then in parentheses, I would do negative 14 divided by 12. And I would get a base of 0.445. Okay, so I wanted to put this problem on there because I wanted to make sure that you were familiar with different ways that the exponent or the base could be expressed. Okay, I'm going to quickly do number 5. This problem is actually something that you would have seen in Algebra 1. It's not something that we really spent a lot of time talking about. You're given some data on the height of an object that's been projected into the air over time. And so you're given lots of different times in the height of the object. You're given a scatter plot so we can see that the object goes up and then goes down. And it asks us to determine the rate of change between two time intervals, or between two time intervals. Remember, rate of change is slope. So even though this data is curved, what I'm asked to do is find the slope between these two values, between 0.3 seconds and 0.6 seconds. So let me just take a look at my table. I'm looking at the slope between these values. Or in terms of my graph, this is 0.3 and 0.6. I'm looking at the slope of the line here. Okay, so I'm looking at the rise over the run. Or if you remember, the slope is just the change in the y values over the change in the x. Well, here's my x, here's my y. So the change in the y values, it doesn't matter what order you go as long as your order is consistent. So for example, I can go 5.76 minus 8.64 as long as when I'm looking at the change in x, I do 0.3 minus 0.6. And when we evaluate this, and I'm going to put everything in parentheses, my numerator 5.76 minus 8.64, and I want to divide that by 0.3 minus 0.6. Now I can tell from my graph that this answer should end up being positive because the slope is increasing between those 2 points. And so we get 9.6. I also have to consider my units. Well, remember, the y is going to go on top, the x is going to go on the bottom. The units for y are feet, the units for x are seconds. So this is going to be 9.6 feet per second. Okay, I'm going to do the same thing for part B, the rate of change from 0.9 to 1.2. Well, 0.9 to 1.2 is this interval here. And again, I'm going to do the same thing, change in x, change in y. So my slope, or the rate of change, and again, it doesn't matter what order you subtract as long as you're subtracting in the same order. So again, I'm just going to go 8.64 minus 5.76, and underneath I'm going to have 0.9 minus 1.2. And if I do this on my calculator, 8.64 minus 5.76, and then I'm going to divide that by 0.9. That should be a minus, sorry, minus 1.2. Make sure you have parentheses around your numerator and your denominator. And notice this time it's negative. And that makes sense because if I'm looking at my time interval from 0.9, let's see, it's hard for me to see on my paper, but 0.9 I think is right here, and then 1.2 is right here. And since that's going down, I would expect it to be negative. So negative 0.96, and again, my units are going to be feet per second. It's always going to be the y units over the x units. It says to compare the rates of change. Well, the rate itself is going to be the same, right? I mean, they're both traveling the same distance over the same amount of time, except in part A, the object is increasing, and in part B, it's decreasing. So the rates are the same. Let's see. So, but for the first interval, the object is increasing. And for the second, it's decreasing. Now, when you're comparing these values, if there's a difference, like if in one case it's traveling at a rate of 9 feet per second, and then in the other it's traveling at a rate of 6 feet per second, then you just find the difference and say the difference is 3 feet per second. So when you're comparing them, the comparison may be different on the test. I just want to point that out. They're not necessarily going to just be opposites of each other. Okay, so this concludes part 2 of the unit review. There'll be one more video on transformations and function operations, but I hope this was helpful.